Today we're going to be looking at piecewise functions. We've already looked at the graphs of piecewise functions in Module 1, but now we're going to try to graph a few on our own and really focus on the equation. So when we have a piecewise function, the first part of it is just the function pieces. This is where we take an equation of a function and then we restrict its domain. So that makes up the second part. We restrict the domain and then just piece them together. So what you'll notice is that the domains don't overlap. They're always going to go order from least to greatest, or smallest x values to the greatest x values. So in this function we have two different pieces. The part where our domain splits is at x equals 1. So we'll see that split here. So I'm going to take that 1 value and put it in the middle of my table, because we have a part where x is less than or equal to 1, and then a part where it's bigger than 1. These values that I'm going to choose for x are going to be -2, -1, 0, and +1. But once I get to 1, we're going to swap to our other function because we want all the x values that are greater than 1. So that would be 2, 3, 4, and so on. So when we are evaluating, we take our x value and we plug it into our function, but only for the domain that it exists in. So when I see x equals -2, oh, it exists in this first domain because it's less than +1. So I'm going to plug it into this part of the function. So I would say -2 squared. We get a +4 out. We cannot plug it into this second function, or second part of the function, because x is not greater than 1. So it would not exist here. Then we get to -1, and we plug that into the first part again. So -1 squared is going to be +1. 0 squared is just 0. And +1 squared is +1 again. This is where it's a little bit special, because that's where our graph switches into this first part and the second part. So I actually want to plug it into both. So I will plug something into this second part of the function. But the main thing here is this is going to be a closed point on my graph. And it's closed because this is where I said x can equal +1. It doesn't get to equal +1 on the second part, but I do want to plug that in, and we'll see why here graphically in a second. So I'm going to plug it in to the second equation to see what we get. 2 times 1 plus 1 is going to be 3. This is going to be an open point at 3 because the function doesn't equal 1 in the second domain. So that makes that an open circle. Then we can keep plugging in other points. So I have 2, and it is greater than 1, so it goes into the second equation. I'd say 2 times 2 plus 1, which is 5. 3, 2 times 3 plus 1, 6 plus 1 is 7. And then 2 times 4 plus 1 is going to end up being 9. So if I graph these, I would take -2, go to 4, -1, go to 1, 0 is at 0, +1 is at +1, and it's a closed circle. It is important to note that there are other values that we didn't plot or didn't put in the table. So just because I didn't write down -3 doesn't mean it doesn't exist, because here any x value less than 1 exists. So I could plug in -3, -3 squared would be 9, and it would just hold that quadratic shape for the left side of the function all the way up until we get to when x is 1. So this is our left side. When x is 1, it swaps to the second equation. And so if I only plotted 2, 3, 4, there would be some things in between 1 and 2 that aren't being plotted. So when we have x equals 1, I have to put our open point here at 3. So I'm going to go to 1, 3, and put my open circle. That tells us that that's what the graph would be approaching, that value, but it doesn't actually equal it since it's not going to have the equal to part in the domain. All right, so 2, 5 is a point on the graph, 3, 7, and then 4, 9. And so our graph will go off like this. Our piecewise function is one whole graph, or one whole function, even though we've taken many pieces and put them together. So I've color-coded them just so you can see the different parts, but it is just one whole function. It is possible that we got a point when we were looking at these and they actually came out to be the same, and so they would overlap and just be continuous instead. We've seen some of those piecewise functions as well. Now let's just try to evaluate this algebraically. So we have a piecewise function. This one has 3 different pieces with 3 different domain restrictions. So we have to consider where is the function going to be evaluated at. So when I see f of 1, that means x is 1, and the function is defined for x equals 1 in the middle section. So I'm going to use that middle piece is going to be x squared minus 4. We evaluate it for when x is 1, so I do 1 squared minus 4. 1 squared is just 1, so 1 minus 4 is negative 3. So when we look at this, f of 1 comes out to be negative 3. I'm not going to plug it into every single equation because I'm only looking for where the function is defined for that domain. When I look at f equals 2, f of 2, when x is 2, this is for the third piece, or the last piece. And that's because it has the equal to section here. So if x equals 2, I'm going to plug it into 1/2 of 2 minus 3 and see what we get out. So half of 2 is just 1. 1 minus 2 is negative 2. So we'd say f of 2 is negative 2. We saw f of negative 5. Negative 5 is going to go into that first part since it's less than negative 3. So that would go into the first part, which was negative 2 times negative 5 plus 7. Negative 2 times negative 5 is positive 10. Positive 10 plus 7 is 17. So we just write out f of negative 5 equals 17. F of 6. 6 is bigger than 2, so it's going to go into that last piece as well, that third piece. So I have half of 6 minus 3. Half of 6 is 3. 3 minus 3 is 0, so f of 6 is going to be 0. All right, so why don't you pause the video and try out the second one with g of x, and then we can press play and check our answers. Okay, so what you should have done in g of 2 would be in that middle section, so I'd be plugging it into negative 2 times 2 squared plus 9. Exponents come first, so that would be 4 times negative 2 is negative 8. Negative 8 plus 9 is positive 1. G of 5, I go into the last one, and there's nothing really to plug in because it's saying for all the values of x bigger than 4, the output's always just negative 5. That's that constant function. Negative 1, if I plug that in, it's still in the middle section. So negative 1 goes into negative 2 times negative 1 squared plus 9. Negative 1 squared is positive 1, but times negative 2 is negative 2. Plus 9 is going to be 7. All right, g of 4, if I plug in 4, it's going to the middle one because that has the equal to. Oh, sorry, at negative 4. Negative 4 is going to move in the first one because it has the equal to. So that would be absolute value of negative 4 plus 5. Negative 4 plus 5 is 1, and the absolute value of 1 is just 1. All right, 0. I'm finding the y-intercept here. So 0 goes into the middle. Negative 2 times 0 squared plus 9 will just be 9. And the last one, it was a little bit different. I wanted to give you something that would challenge you a little bit. So I have these two pieces and I'm going to add them together. So let's find g of negative 9 first. That's going to go into the first one. That'll be absolute value, negative 9 plus 5. That's a negative 4, but absolute value makes it come out positive 4. Plus, and then we're going to find g of 8. That goes into the very last one, which is just negative 5. So when I add those answers together, I get negative 1. There's a little bit something with some function operations in there. All right, so the last part of this piecewise function stuff is really our important applications. So we want to take this and put it into a word problem that we could see in real life. So we have something here about our North Carolina unemployment rate for 2008. It is approximated by this function equation, and it's saying that T is our month in 2008. So January is month 1, so that's when T equals 1. U represents our unemployment rate in percentage form, so it's the unemployment rate in percentage. So if it says calculate U of 4, that's saying that T equals 4. So let's figure out, what does that mean? U of 4 would be plugged into the first one, since that's between 1 and 9. So 0.28 times 4 plus 4.44. We just take that and plug it into our calculator. 0.28 times 4 plus 4.44 is 5.56. So there's our answer, but we want to interpret what does that mean in context. So if T is 4, that's the months after or in 2008, so that's April. So in April 2008, the unemployment rate was 5.56%. So the unemployment rate is in the percent, and we would write it like that. B says we want to use our function notation to approximate the rate in December of 2008. So if we think about what is December of 2008, would mean that T equals, again, the month in 2008, so T equals 12. And we're going to plug that into our equation. Now, I look at this domain and it has the equal to at 12 for the last one, so we were going to take that and do U of 12 equals 0.8 times 12 minus 0.93. Take that and plug it in. And I get 8.67. In this case, the unemployment rate for December of 2008 was 8.67%. Last part here, when in 2008. The when is our key word because that's telling us to find T. So we want to calculate what t value would give us an unemployment rate of 6.12%. This is where piecewise functions are tricky because we have more than one equation and we don't know what the t value is. So it's not where I'm inputting it into a specific equation based on the domain. Now we're trying to figure out the t value. So we're going to have to plug it into both parts of the function and evaluate the domain. So if I have 0.28t plus 44, or 4.44, we want to see, will that come out to be 6.12? If I solve this out, we do 6.12 minus 4.44 to get 1.68. So now I have 0.28t. I'm undoing the multiplication by dividing. So 1.68 divided by 0.28 comes out to be 6. So t equals 6. Now the big thing about this is this was our equation on the domain of 1 is less than or equal to t, which is less than or equal to 9. So 6 is inside that domain. So this works in the given domain. So I would say that's one of the answers, but it's not necessarily the only answer. That's because they're not necessarily a one-to-one function. That could happen where this also has an output of 6.12 at some point. So we're going to test out that one as well. So 0.8t minus 0.93 equals 6.12. If I work this out, 6.12 plus 0.93 is 7.05. And then we divide by 0.8, and I get 8.8. So t is 8.8125 technically. All right, let's evaluate this on the domain. So this domain was on the domain of 9 is less than t is less than or equal to 12. We got 8.8. That is not in the domain. So this doesn't work. In the given domain. Which means we only had one answer when t equals 6. So we'd say the unemployment rate was 6.12% and t equals 6. So 6 is June, in June of 2008. All right, our last one here, we're looking at the federal income tax for an individual. And so this one's a little bit trickier. We're having to write the equation this time. We're given our information, but we need to decide what the different breakdowns of the equation pieces are. So if it says that the federal income tax with an income of $0 to $9,325 is 10%, then the incomes greater than $9,325 goes up to this much, has a rate of 15%. So the rate and the tax amount are our variables. So I is going to represent our income. So that's our gross income, and it's in dollars. But T is representing our taxes paid, also in dollars. So it says express taxes paid T as a function of the gross income. So when it says as a function of, that's telling you that's our input. So we want to find T of I. And what we know so far is that we had two different tax brackets, basically, from 0 to 9,325, and then 9,325 to 37,950. So we're going to make up two parts. We have one thing here for if our income was between 0 and 9,325. But then we had a second tax if our value was between 9,325 and 37,950. So 9,325 less than I less than or equal to 37,950. Notice what I did. I put the less than symbol here, but it doesn't have an equal to. And that's because the first domain already claimed 9325. It gets to equal it. So if it's going up to 9325, then this is from 9325 or more, but we're not including the 9325. So those are the domain restrictions, but we want to write the equation component. The first one I think is a little bit more straightforward. It says that if the income is between 0 and 9,000, then the tax rate is 10%. So I would just say 10% of whatever that income is, as long as your income's between 0 and 9325. The second one is a little bit trickier, and that's because it says that the gross income's greater than this, the rate increases to 15%. But that's only for the amount that's between 9325 and 37,950. So when they're calculating your your taxes based on your income, that first amount up to 9,325 is going to be taxed at 10%, and the amount over is going to be taxed at 15%. So I want to pay just 10% of that first initial amount, 9325. And I get 932.5 plus. So this is just going to be the initial amount plus whatever's additional over the 93. So now I'm going to add our 15%. And it's 15% of the amount over 9,325. So if I just put an I here, that's the full income. So I'm taking 15% of my full income plus the additional. We don't want to take more taxes. I only want to take the income over 9,325. So I'm going to subtract out the 9,325 because I've already paid taxes on that. Plus whatever's over is taxed at 15%. So that I think is the hardest one because you do have to subtract out the pieces. But so just to maybe give ourselves a little note of where this came from, this 93 came from the first $9,325 of the income taxed at 10%. That's where that gave us 932.5. So it makes a little bit more sense when we look at an actual person's income. In B, we have a person's income is $12,000. So if I was taxing $12,000 of income, the first initial is going to be 10% on that 9,325. So that is 932.5. So $932.5 plus 15% of everything over 9,325. So I had $12,000 and I'm subtracting 9,325 because I've already taxed some of it. We're only taxing the amount over at 15%. If I put this on my calculator, 932.5 plus 15%, so 0.15, of 12,000 minus 93.25 gives me 1333.75. So an individual who has $12,000 gross income pays $1,333.75 in taxes. The last one says, what was the gross income of an individual who paid $850 in taxes? So you can try out both equations, but this one helps when I know what the income's coming from. So 850 is less than this initial amount. And I know if my income's bigger than 9,325, I'm automatically going to pay $932.50. So it's got to be coming from the first one. So let's try it out. So 0.10 times I equals 850. We would divide by 0.10 and get I equals, and we can just put that in our calculator as well. So 850 divided by 0.10 is 8,500. $8,500 is within that domain restriction that we had. Now we could try out the other one and I'll show you why it would not make sense. All right, so we want this to equal 850. So if I work this out, the first thing I'd be doing is subtracting 932, so 850 minus 932.5, so 0.15 times I minus 9325 equals negative 82.5. Then I'm going to divide by 0.15, so I minus 9325 equals. So I'm going to take that and divide by 0.15. I get negative 550. The last thing we're going to do to get I by itself is add 9,325. So plus 9,325 gives me 8,775. So 8,775. This does not work in the domain that we were given for that second one. So that is not in the domain. So it's not possible that it's going to equal it in the second one. The only way that we had $850 of income tax was if the income was $8,500. So there are a few of these in our lab manual for you to practice as well.